Last class, we went down to the physical layer and A2I2 port, the cables and connectors that carry your bits. Today, we move up one level to the device that sits at the very center of every local network and quietly makes it work, the switch. You've used switches your whole life, probably without a second thought. The box your office computers plug into, the ports on the back of your router at home and A200 well. Those are switches. Their job sounds simple. Connect the devices on a local network so they can talk to each other. But how a switch does that job is genuinely clever. And understanding it explains a huge amount about how networks behave. A switch is not a dumb splitter that shouts every message to everyone. It is a smart device that learns exactly which device is plugged into which port and then delivers each message to precisely the right destination and nowhere else. Today, we will open the switch up and watch that intelligence at work and 8200 toolhunter addresses, the address table it builds, how it forwards a frame, what it does when it does not yet know the answer, and how it differs from its cousin the router. By the end, the box at the center of the LAN will hold no mysteries. Let us begin. Here is our path for today. First, what a switch actually does. Second, MAC addresses. Third, the MAC address table. Fourth, how a frame is forwarded. Fifth, flooding and 8012, handling the unknown. And sixth, how a switch differs from a router. Let us dive in. Let us start by understanding what a switch is for. And we will do it by contrast with the device it replaced. Long ago, local networks used a device called a hub. A hub was simple to the point of being dumb. Whenever a frame arrived on any port, it copied that frame out of every other port. Everyone received everything, whether it was meant for them or not. Imagine a room where, to speak to one person, you had to shout so all 30 people heard you. It worked, but it was noisy, wasteful, and it did not scale an 81812. Every message collided with every other. A switch replaces that shouting with precision. When a frame arrives, the switch sends it out only the single port where its intended recipient is connected. Everyone else hears nothing. It is the difference between shouting across a room and quietly handing a note directly to the one person it is for. The network instantly becomes calmer, faster, and far more scalable, because ports are no longer fighting over shared airtime. This precision is the entire value of a switch, and it raises the obvious question that the rest of the class answers. How does the switch know which port the recipient is on? A hub did not need to know anything, and 81212, it just copied blindly. A switch has to be smart. It has to learn the layout of the network and remember it. That learning and remembering is the magic we are about to unpack. So the takeaway, a switch connects the devices on a local network and, unlike the old hub that copied every frame to every port, it delivers each frame only to the exact port its recipient is on, an 8202 precise instead of noisy and 8200200, which raises the question of how it knows where everyone is. To deliver a frame to the right device, a switch needs a way to name devices and 8200 and that name is the MAC address. Every network device, an 82112, every laptop, phone, server, printer, and 82112 has a MAC address built into its network card. It is a unique hardware identity, assigned when the card is manufactured, and it stays with that piece of hardware. Think of it as the device or T9's permanent physical name on the local network, not where it is, but who it is at the hardware level. This is the address a switch works with. Recall from the encapsulation class that a flame and 8 hodupol, the layer 2 unit and 8 hodupol, carries a source MAC address and a destination MAC address. When a device sends a frame, it stamps on the destination MAC of who it is for and its own source MAC as the sender. The switch reads these addresses to do its job. MAC addresses are the language of the local network. It is worth pinning down the distinction that trips people up. A MAC address is a hardware identity, permanent and local, while an IP address, an 802 from earlier classes, and 802 is a logical, changeable address used to route across networks. On your local network, the switch delivers by MAC address. crossing between networks is the router a 9-ICE job using IP. 2 addresses, 2 layers, 2 purposes, and A212. And today, we are firmly in the world of MAC. So the takeaway, every device has a MAC address, and A212, a unique hardware identity built into its network card, and A212, and because each frame carries a source and destination MAC, the switch uses it as the local delivery address, distinct from the logical IP address used to route between networks. Knowing devices have MAC addresses, the switch now needs to remember which device is on which port. It does this with the MAC address table. The MAC address table is simply a lookup. It stores which MAC address lives on which physical port of the switch. Port 1 has this device, port 2 has that one, and so on. This table is the switch ND9, a entire map of the local network and 8200, the knowledge that lets it deliver frames precisely instead of blindly. Without it, a switch would be no better than a hub. The beautiful part is how the table gets built. The switch learns it automatically by watching. Every frame that arrives carries a source, MAC address, and 8000 tuple. The sender NE tuple, S, identity, and A tuple, and it arrives on a particular port. So the switch reasons, an 8020 sec, I just saw a frame from this MAC come in on port 3, therefore that MAC must be reachable through port 3. An 82120, it records that, and now it knows. It does this for every frame constantly, so the table stays current as devices come and go. This is called learning, and it is what makes a switch plug and play. You do not configure the table by hand, you just plug devices in, and as they start sending traffic, the switch quietly maps out who's where. Within moments of activity, it knows the whole local layout. That automatic, self-building map is the heart of a switch N39's intelligence. So the takeaway? The MAC address table maps each MAC address to the switch port it lives on, and the switch builds it automatically by noting the source address and arrival port of every frame NA212. A self-learning map that makes the switch plug and play, with no manual configuration. Now, we can put it together and watch the switch do its core job, forwarding a frame to the right destination. It is a keen 3-step sequence. First, a frame arrives, and the switch reads its destination MAC address and A212, the identity of who the frame is for. This is the question the switch must answer. Where does this need to go? Second, the switch looks that destination MAC up in its address table. If it has learned that address, the table tells it exactly which port the recipient is on. Number, this lookup is fast and A2R2L. It happens in hardware, at wire speed and A2R2L, which is why a good switch can handle enormous volumes of traffic without breaking a sweat. Third, the switch sends the frame out that one port, and only that port. Every other device on the switch hears nothing of it. The frame goes straight from sender to recipient, privately and efficiently. Read the destination, look up the port, forward out one port and 820 that is the whole job of a switch. Perform millions of times a second invisibly for every conversation on your network. It is simple in principle and stunning in execution. So the takeaway? To forward a frame, the switch reads its destination MAC address, looks up the matching port in its address table, and sends the frame out only that one port and 8212. A fast, hardware speed, red lookup deliver loop that keeps every conversation private and efficient. There is one case the forwarding steps do not cover. What if the switch reads a destination MAC that is not in its table yet? Its answer is called flooding. When a frame in array E, destination is unknown array ESP, because that device has not yet sent any traffic for the switch to learn from array at ESP. The switch cannot look up a port. Rather than drop the frame, it does something pragmatic. It floods the frame out every port, except the one it arrived on. In effect, it says NA 2020, I do not know where you are, so I will deliver this everywhere and let the right device pick it up. NA 2021, for that one frame, the switch behaves briefly like the old hub. But here is the clever twist. The recipient, upon receiving that flooded frame, will usually reply. And that reply is a frame with the recipient and MAC as its source, arriving on a specific port. The switch, always learning, immediately records NIT 200, 200, 200. That MAC is on this port, NIT 200, 200. So the very act of flooding leads directly to learning the answer, NIT 200, 200. The next frame to that device would be forwarded precisely, no flooding needed. This is why a switch is efficient, even though it starts out knowing nothing. Flooding is rare and self-correcting. It happens only for genuinely unknown destinations, and each occurrence teaches the switch so it does not happen again for that device. The network quickly settles into precise, learned forwarding, with flooding as the brief exception that fills in the gaps. So the takeaway, when a destination MAC is unknown, the switch floods the frame out every port except the one it came in on, then learns the correct port from the recipient and IT9 supply and IT912. A rare, self-correcting fallback that quickly turns into precise, learned forwarding. To really understand a switch and auth heist effect on a network, it helps to see how it carves the network into domains and a tau 1. And there are two kinds to distinguish. First, each switch port is its own collision domain. In the old hub days, every device shared one wire, so two devices sending at once would collide and have to retry an A212 hole, and the more devices, the worse it got. A switch gives every port its own dedicated connection, so a device never has to compete with others for the wire. Collisions essentially disappear, which is a huge part of why switched networks are so much faster than hubbed ones. But an A2112, and this is the important limit, an A2112, all the ports on a switch remain in a single broadcast domain. A broadcast is a special frame meant for every device on the local network, and by design, the switch sends a broadcast out of every port. So while ordinary traffic is neatly isolated to individual ports, broadcast traffic still reaches everyone connected to the switch. The switch tames unicast noise but not broadcast noise. This distinction matters because on a large network, broadcasts can pile up and affect every device, and a plain switch cannot contain them. It tells you where a switch N39S power ends. It perfects local, one-to-one delivery, but the network-wide broadcast remains a shared, network-wide event. Solving that requires either splitting the switch logically or moving up to a router and A212, which points us to our last two ideas. So the takeaway, a switch makes each port its own collision domain. So devices never fight for the wire, and collisions vanish and A200. But every port stays in one broadcast domain, so broadcast frames still reach all of them. The switch tames unicast traffic, not broadcasts. We have mentioned the router several times. Let us now draw the line between the two clearly, because confusing them is one of the most common beginner mix-ups. A switch operates at layer 2, the data link layer. It moves frames, and it makes decisions using MAC addresses entirely within a single local network. Its whole world is one LAN. It connects the devices in your office or your home to each other, and it is superb at that. But a switch has no concept of reaching a different network, an 8212. That is simply not its job. A router operates one level up, at layer 3, the network layer. It moves packets, and it makes its decisions using IP addresses. And crucially, it works between different networks. A router is what connects your local network to another network, and ultimately to the internet. Where a switch delivers within a LAN, a router forwards between LANs, choosing the path a packet takes across the wider world. The clean way to hold it, a switch connects devices into a network, a router connects networks to each other. In your home, that little box does both jobs in one unit, and 8212. The switch ports connect your devices, and the router part links them all out to the internet and 8212, which is exactly why people blur the two. But they are distinct roles at distinct layers. MAC and frames within, IP and packets between. Keep that split clear, and a huge amount of networking falls into place. So the takeaway, a switch works at layer 2, forwarding frames by MAC address within one local network, while a router works at layer 3, forwarding packets by IP address between different networks, and A212. A switch connects devices into a network. A router connects networks to each other. Let us close with a feature that shows how flexible modern switches are, the VLAN or virtual LAN. Normally, every device plugged into a switch is part of one single local network and A212. They can all reach each other, and they all share one broadcast domain. A VLAN lets you take that one physical switch and divide it in software into several separate logical networks. Ports 1 to 10 might be one network, ports 11 to 20 a completely separate one, and A212. Even though they are all in the same physical box, the switch keeps their traffic apart, as if they were on different switches entirely. Why is that useful? Two big reasons. Security and isolation. You can put sensitive systems on their own VLAN, cut off from the general network, so a problem in one group cannot spread to another. And order. You can group devices logically and ATID to full, by department, by function, by trust level, and ATID to full, without running separate physical cabling and buying separate hardware for each group. You get the separation of many networks from the cost of one switch. VLANs also help with the broadcast problem we raised earlier, because each VLAN is its own broadcast domain. Splitting a big network into VLANs contains broadcasts within each group instead of flooding the whole thing. It is a beautiful example of the theme of this class, an A212 A switch is not a dumb box but a smart, configurable device that shapes how your local network behaves. Master the switch, and you control the heart of the LAN. So the takeaway, a VLAN divides one physical switch into several isolated logical networks in software and 8200 pole, giving you security through isolation and logical order without extra cabling or hardware, and containing broadcasts by making each VLAN its own broadcast domain. Let us gather the whole class in one breath. A switch delivers each frame only to the port that needs it, and 8202, a smart hub, precise instead of noisy. MAC addresses are the unique hardware identities the switch delivers frames to. The MAC table maps each MAC to a port, learned automatically from every frame and tiny 9 source. To forward, the switch reads the destination MAC, looks up the port, and sends out just that one. For an unknown destination, it floods to all ports, then learns the right one from the reply. And a switch moves frames by MAC within a LAN, while a router moves packets by IP between LANs. Next class, N81212, routing, how packets find their way across networks. One idea at a time. That is the switch,